In this video, we will be looking at alternating current and how it is used to transmit electrical potential energy over large distances. Remember that there are two types of current: DC direct current, which flows in one direction only, AC alternating current, which changes direction many times per second. In South Africa, the frequency of AC or alternating current supply is 50 Hz. This means that there are 50 back and forth cycles per second. Let us look at a comparison between AC and DC current. When looking at the table of comparisons, we can see that AC definitely has an advantage over DC in the fact that it can travel over large distances safely. AC also provides more power than DC. South Africa is coal dependent, with almost 90% of our power supply provided through the burning of coal. Most power stations are in the rural areas, so the electrical potential energy has to travel over large distances to the end users, be it a family home or some form of industry. Because alternating current can be used in a transformer and stepped up to a higher voltage for long distances, it's ideal. When it's ready to be used in a home, it is stepped down again to make it safer again. Let's see how that works. The voltage is stepped up after leaving the power station in a transformer. The electrical potential energy is then transformed over large distances and then stepped down, that is decreased for use by industry and for use in our homes. A transformer is a device which can change the voltage. They work on the basis of electromagnetic induction. They only work when transforming alternating current, since they require a changing magnetic field. So, in conclusion, the main advantage of AC is that the voltage can be changed using transformers, devices used to increase or decrease the amplitude of an AC input. This means that the voltage can be stepped up at power stations to a very high voltage so that the electrical energy can be transmitted along the power lines at low current and therefore experience low energy loss due to heating. The voltage can then be stepped down for use in buildings, street lights, and so forth. As we already know, alternating current changes directions many times per second. We call this an oscillating current. Both voltage and current vary sinusoidally. Think maths sine wave with time. The DC current is constant with respect to time. The power provided by an alternating current with a maximum current value, Imax, is not the same as the power produced by the current of the same value. The reason for values for DC and AC maximum differing is because AC is only maximum for a very brief period of time per cycle. This is why we use the average value of the current, which is referred to as root mean square or RMS current. Similarly, the RMS voltage. The root mean squared values are equivalent to what the DC values would be. The equations are, for current, I RMS is equal to I max over the square root of 2. Similarly, voltage RMS is equal to the voltage maximum over the square root of 2. So, when we say that the voltage supplied to our homes is 240 volts, we are talking about root mean square voltage. Manipulating the formula to solve for the maximum voltage, we say V RMS multiplied by the square root of 2 is equal to 240 volts times root 2, giving true maximum voltage of 330.4 volts. In other words, if you had two circuits, one DC and one AC, and you wanted them to use exactly the same amount of power, or energy per second, then you would use the DC values of the current and voltage to be the same as the RMS values of current and voltage in the AC circuit. The power being used in each circuit is the same, so you can use all your old electrical equations. If we draw the graph of power versus time for an AC circuit, we notice that it fluctuates with time as shown in the graph. Power is, however, always positive. As power fluctuates with time, it is useful to consider the average power in an AC circuit. P average is taken as half the peak of the value of power. Whenever the values for voltages and currents are specified in AC circuits, they refer to the RMS values, and the power value is an average power. Let us look at a few examples. Number 1. An electric stove is marked with 2,500 watts, 220 volts. A. Calculate the maximum voltage through the stove. B. Calculate the resistance of the stove. First A. The maximum voltage. Substituting the value for the RMS voltage, we see that the maximum voltage is solved by multiplying out by root 2, and the maximum voltage in the stove is 311.13 volts. B. When calculating the resistance of the stove, remember that the stove is marked in RMS values, so we can only use those to calculate the resistance. So we could find the current and then use the Ohm's law, or we could directly go to the equation as power RMS is equal to V RMS squared over R. Substituting the 2,500 RMS power in and the 220 volts RMS squared, solving for resistance gives us 19.36 ohms.